So fungi are everywhere, including in this room. But the ones you've probably seen are going to be Basidiomycetes, which we commonly call mushrooms. And these are a few that I photographed in my front yard in a particularly wet season. But most of these types of organisms we don't consider particularly dangerous, although Charles VI would had disagreed for a few minutes after he ate his bowl of death cap mushrooms. But most of the fungi that we really worry about are actually ones that you can't see. And warning, I am going to show a few gross pictures in this next slide. But the ones we're worried about are microscopic. And they're shown here. For example, they cause things like ringworm, and to my right over here, or to my left over here, thrush, which is caused by an organism called Candida. And so these guys are small, but they cause big problems. And they're the ones that can cause even life-threatening infections. Most of the life-threatening and fungal infections we worry about are actually in the immunocompromised. These would be with patients that have cancer chemotherapy, organ transplants, HIV, AIDS, things like this. But they can also cause what we call superficial, not in importance, but in skin, surface infections and oral infections, vaginal infections, etc. The fungus that I work with is called Candida albicans. It's the cause of the largest number of infections because it's involved in causing over 100 million vaginal infections, and amongst immunocompromised people, it can cause tens of millions of oral infections and over 400,000 life-threatening invasive infections, which are the ones that my lab is focused on the most. Now, Candida is a shapeshifter. It can grow as a rounded yeast form, like you see on this panel, and this form is sort of considered the commensal form because this organism is a commensal. It lives on us and in us, which is the reason why it's so common. But it also grows these elongated hyphal shapes, which can pierce tissue and do damage. So how do we deal with the fungus? Well, we've created antifungals, not me, but industry in general. And these mostly target, there's three main classes, and they mostly target the cell envelope, which is a combination of a membrane and a cell wall that surrounds the outside of the fungus. Now, the structure of this is shown in this cartoon. The membrane, which is at the bottom, that's shared with all living cellular organisms, including us, but the fungal membrane is a little different. But what they have that we don't have is this thick cell wall, which is a very rigid surface, or very tough, that's on the outside, and that actually has a number of good targets for antifungals, both realized and potential. Now, and some examples of these antifungals include amphotericin B, which this works by targeting components in the membrane that are different than ours, and the model is that it punches holes in the membrane. And so basically the insides of the cell leak out and the cell dies. And this is a pretty effective antifungal. The azoles are also very commonly used. Diflucan's a common name for it. It targets the membrane also, but it inhibits it from actually being able to expand. And so as a result, the fungus doesn't die, it just can't grow. And so over time, the immune system or the body can eliminate it with given enough time. Now, the type of antifungal we've been focusing on in my research is the echinocandins. These target the cell wall, which we don't have. They're very effective, and what they do is they cause the inhibition of a key component of the cell wall called beta-1,3-glucan, which is shown here in green. It's not really green, but but what happens is as it decreases in amount, the cell's pressure grows and it explodes. And of course, with these antifungals, we think, oh, we've won the battle, except that the fungus doesn't really like it that way. And like many microbes, we're having the growing specter of antimicrobial resistance rising. And so they have a number of ways of resisting our drugs. And so I'll tell you about a few of those. For example, in a moment, we have the azoles. So the azole class, the main mechanism of resistance in many cases is a membrane-bound pump. It's a little protein that actually can pump the drug right back out of the cell. So the concentration of the drug never gets high enough in the cell to kill it, and so as a result, you have to switch to a different kind of drug. In addition, there's resistance to the echinocandins. In this case, this little green barrel is supposed to represent the synthase that makes the beta-glucan. There's a square little antibody that binds, or not antibody, but drug that binds to it, but mutations in that change the shape of the protein, and now the drug can't bind to it anymore, so it can keep on making a cell wall and survive. Now, amphotericin B is not generally involved in resistance, but the drug itself is somewhat toxic. It's actually more so in adults. It doesn't seem to have as big of an effect in children, but it's nephrotoxic, damages the kidneys, hence the nickname amphoterrible. And so the drug of use of this is a little bit limited. There's also cases of treatment failure where there's no obvious resistance. One explanation for this might be that because of the infection causing these spots in tissues during systemic infections, the drug can't really get into it very well because it's occluded. And so this is where our research has started to focus, is how can we take advantage of things like this bottom point, the immune system, to try to couple the drug with the immune system. The perfect drug for doing this, we think, is the echinocandins. And the reason is the echinocandins damage the cell wall, and the cell wall, then the fungus tries to repair itself. And as it's trying to repair itself, what ends up happening is that there's an exposure of certain epitopes. To the right, you see, my right, do you see what we picture as the cell wall being deformed? This exposes this beta-glucan, and the immune system can see it better. This could enhance the response. What my lab's been studying is how does this process of shaping the cell wall occur? An example of this, some of the experiments we do, in the top you see untreated, and the bottom you see treated. We have a probe that detects the beta-glucan. It is not binding as well on the top, but it binds better in the bottom because you get exposure. And the idea is that the immune system can see it better and therefore might respond. So even if the drug concentration is not getting high enough, the immune system could come in and mop up what we don't take care of. And so we're working on the proteins that cause this exposure to happen in the fungus, and also trying to better understand how the immune system sees this exposure and then attacks it and destroys it, with the hope that eventually we can help contribute to better outcomes. Thank you all very much.